One qubit, not so bad. We went through one qubit and how to use a Hadamard gate or other gates, which is really just a laser manipulating the qubit to other states. Now we want to consider two qubits. Seems easy, but I've been struggling over it for quite a while. So either I'm not so smart or it's pretty difficult to put the stuff together. So let me start with some pictures and diagrams so you won't have to just look at my face. Here are the two basis states of qubits. This 0, which is at the top of that block sphere, and 1, which is at the bottom of the block sphere. And you'll notice there's just a 1 and a 0 and a 1. So those seem pretty simple. Of course, in between, it can be different values. It could be complex numbers and all sorts of stuff. But these are the two basis states. Now let's go on to a 2-qubit system where we're looking at 2 bits at a time. Here's a 0 and a 1. And then there's this little circle with an X in it. This means to take what's called the tensor product, T-E-N-S-O-R, the tensor product. And this will give us the representation of a 0, 1, 2 different qubits. Of course, you can have 0, 0, 0, 1, which is shown here, 1, 0, or 1, 1. So let's try to get our heads wrapped around this part of it. If this is a 1, 0 and this is a 0, 1, how do we come up with this relationship? Well, the 1, 0 says that we're going to multiply 1 times this vector, which is a 0, 1, so we got a 0, 1, and the bottom part, which is a 0, 0 times the 0, 1. So that makes that all zeros. So that's the way it works out. Now, to make it a little bit simpler, let's look at all of them. These are all the possibilities of the basis gates. In other words, just zeros and ones for 2 qubits. There's our 4 vectors. Now notice there are 4 items in each one. So that means it's 4-dimensional. So it's quite a bit more complicated. If we go to 3 qubits, then it's 2 to the 3rd, or we're going to have 8 dimensions. And that doesn't go from 4 to 6, it goes from 4 to 8 dimensions. So it gets really complicated. So let's stick with just 2. I'm going to go through an overview, and then I'm going to break it down into little teeny tiny pieces. We're going to try to create superposition, not with just 1 of these qubits, but with 2 of the qubits. And here's the steps that are going to be taken. Here's that little X, which is this tensor product. This is H, which is a Hadamard gate, which is a 2 by 2 matrix. And then this I is the identity matrix. What this process does here is it creates a 4 by 4 operator, can operate on this 0, 0 2-qubit system, and this is what we come up with. Now, I'm going to go through the details. I don't want to hide it, but let's just look at this and see what it looks like. It looks very similar to superposition of 1 qubit, except that there are 2-qubit systems here. And each one of these can be represented by a 4-dimensional column vector. The 4-dimensional column vector here would be 1, 0, 0, 0, 0. The 4-dimensional column vector here would be 0, 0, 1, 0. Now, you might say, oh, these two things are tied together now. But look, the second qubit did not go through any superposition. The first qubit is in superposition, but the second qubit is not. And another thing is, we can write it as this relationship right here. If we take this, take the tensor product times a 0 qubit, then we come back up here to this thing right there. The important part is it says no entanglement. Now for the details. This is the Hadamard gate that we used before, and this Hadamard gate is going to be applied to just the first qubit, and the second one is going to be left alone. And the way that we do that is we use this identity gate. In other words, if you take a vector and multiply it by the identity, you get that same vector right back at you. Now, when we take the tensor product of it, we take 1 times the identity. Here's 1, 0, 0, 1. 1 times the identity, 1, 0, 0, 1. 1 times the identity, 1, 0, 0, 1. And minus 1 times the identity. So we have minus 1, 0, minus 1. So here's this big 4 by 4 matrix that's going to be used as an operator on the vector 0, 0. And what's 0, 0? 1, 0, 0, 0. So if we take this and operate on that, it's only going to change 1 bit. Here's a example. It uses a little bit different one. Instead of 1, 0, 0, 0, we're using 0, 1, 0, 0, which would be the basis state of 0, 1. And if you go through this thing, you will take this column times the first row, matching the elements up. 0 times 1 is 0. 1 times 0 is 0. 0 times 0 is 0. So this first element here is 0. Then you take it and multiply times here, and we get a 1, because this 1 will match up with that 1. Here's where that 1 comes from. Then we multiply this 1, and everything zeroes out in this case. So there's a 0, and here we have 0, 1, 0, minus 1, which still gives us this 1. Now, if that isn't too much gobbledygook, you can think of this as 0, 1, 0, 0 plus 0, 0, 0, 1, which would be these two states. And what I want to point out again in this case is that the second qubit did not change. So we need something that'll make the second qubit change so that both the first and the second show that superposition. Okay, here's our setup that we just went through. Here's the combination of 0 basis state and 1 basis state all combined together, which is just what we came up with that has that superposition. Now, if I take the C0 gate, which we kind of have to look through here. Here's the C0 gate. Notice it's like the identity, but these last two are flipped around. This allows us to flip the bit, which is, see what it did? It was 1, 0. Now it switches it around to 0, 1. And now we have this as our final state, which is entangled. And this happens to be one of the 4 possible Bell states. This is entanglement. Notice the 0 in just these two qubit systems. We have the 0 is in superposition somewhere between 0 and 1. 1 over square root of 2 happens to be the case, and this one is 0 to 1. The second qubit is also in superposition, and this happens to have this process called maximally entangled. As I mentioned before, there are 4 possible Bell states. Here's all 4 of them.